Automated environment reduction for debugging robotic systems. Here we see a basic failure when testing a robot system's navigation towards a goal. The robot narrowly fails to traverse a ditch and is unable to actuate further. Viable paths exist, but it doesn't seem to be able to find them. The debugging process includes the collection and examination of many topics, traces, diagram analysis, and root cause hypotheses. How do we simplify what we're looking at? The original scenario generates too many hypotheses because the complexity of the environment is compounded by the complexity of the system. In the reduced scenario, we can clearly see that the scan data leading up to the failure was all infinite values, giving no indication that a ditch was present. This suggests fixes such as angling the scanner or incorporating the IMU gyroscope in path planning, or eliminating the test altogether as it doesn't fit the limitations of this build. So our givens are an environment E where robot R fails with failure F. We know that critical environment elements sit side by side with irrelevant ones. Then how do we remove the grayed out regions? We have several sources of data we can use to get there. Information from the robot, information from the failure, and elements of the world. Traditional software debugging approaches do not leverage the temporal and spatial relations essential to environment reduction. Using givens of E, R, and F, we want to arrive at an environment E prime that causes F where E prime is a subset of E. Our environment reduction takes cues from established software debugging techniques. We leverage the temporal and spatial relations to heuristically reduce the environment and compare the results against the original failure. First, we systematically reduce E to subenvironments, using partitioning and prioritization heuristics that incorporate prior knowledge from previous runs. For example, we partition on the proximity of elements in the environment and prioritize according to how close those partition centroids are to the trajectory of the robot. The second step reruns the test on the set of subenvironments, using an oracle to check for similar failures. As we go, we partition with increasing granularity, performing a depth-first search for a minimal failure-inducing world. We arrive at a minimal failure-inducing world when all subenvironments of the subsequent partitioning have produced a result dissimilar to the original failure, and our partitioning size is equal to the number of elements in the world. For further detail, refer to algorithms 1 through 3 in the paper. As the algorithm progresses, it will encounter runs in which the manipulated environment is either a success or a dissimilar failure. Once a similar failure is reached, repartitioning is triggered and that world becomes the new candidate for the minimal failure-inducing world. The process is repeated until a stopping condition is met. As the plot shows, environment size is monotonic decreasing. Applying this technique to 3 separate scenarios, we arrive at a collection of minimal worlds with reduction ranging from 76 to 96%. We introduced a novel technique for environment reduction to assist the debugging of robot systems, the results of which are promising. Thank you.